ろしくお願いします。今日は英語で発表させていただきます。Okay, so I'm Will Haku, and today I'll be talking about learning discrete representations via information maximizing self-augmented training. And this is a joint work with Takeru Miyato, Seiya Tokui, Eiji Matsumoto from Prepared Networks, and my advisor, Masashi Sugiyama. So in this talk, I'm going to talk about our method on unsupervised discrete representation learning. So the task is that we're given unlabeled data, which is often abundant in real application, and our goal is to learn a function that maps each of these unlabeled data into discrete representations. And in particular, we want similar data to be mapped into similar representations, while this similar data to be mapped into dissimilar representations. This is a pretty general machine learning task that includes two machine learning tasks as special cases. First, it includes clustering. A clustering basically maps each data into the cluster that data belongs to. And this cluster assignment of each data can be considered as discrete representation of data. Second, it includes the task of hash learning when we consider mapping from each data into binary codes like this shown in this slides. And hash learning is widely used in large-scale information retrieval. So by solving this unsupervised discrete representation learning, we can solve this important machine learning task simultaneously. And so now we want to model this, how to map this unlabeled data into discrete representations. So deep neural networks are promising to be used for this mapping function because they are flexible, they can model very complicated nonlinear function, and also they can easily scale to large data sets. However, the challenge of using deep neural networks for this mapping function is that the prediction of deep neural networks are often sensitive to input perturbation. So let me illustrate this using the toy data sets. So consider this kind of spiral-shaped data set which has this kind of cluster structure, and we want to cluster them. And in particular, our goal is to learn this probability P of y given x that takes the input data as input and output the cluster assignment probability. And we model this function by deep neural networks. And using to learn this function, information maximization is often used. So in information maximization, we want to learn this mapping function such that the mutual information between input data x and the cluster assignment y is maximized. However, when we use this criterion to train the deep neural networks, we often get this kind of undesirable decision boundary that does not really find the good cluster structure in this toy data set. So in particular, when we consider this data points in this black data points, and when we perturb just a little bit, the cluster assignment can change drastically, which is not really appropriate for real applications. So to mitigate this problem, regularized information maximization was proposed. And in this framework, in addition to maximize the mutual information, it also tried to regularize this mapping function by sort of incorporating the prior information of what the mapping function should be. And in original work, the weight decay regularization was used. So it's basically a L2 regularization on the parameter of the neural networks. However, still, we see in the right figure that we are unable to learn the good cluster assignment, cluster that really capture the cluster structure of this toy data set. So our contributions are twofold. So we built on this RIM framework, and we proposed a novel method called IMSAT. So our two contributions are orthogonal. First, we propose a better regularization method to better regularize the neural networks. And we also extend the mutual information maximization criteria that can be also applied to the task of discrete representation learning, not just clustering. And by using our method, IMSAT, we are, as shown in the right figure, we are able to learn cluster boundary, decision boundary that is able to capture the cluster structure. And as we see, when we take the data points, when we perturb just a little bit, the cluster assignment does not really change in this right-hand figure case. And we also see that we are not only able to learn the cluster assignment, but also able to learn the hash function, so mapping each region into binary codes. And experimentally, we are able to achieve state-of-the-art performance on both the task of clustering and hash learning. So in particular, for MNIST dataset, which is a handwritten digit recognition dataset, we are able to find clusters that almost perfectly correspond well to the ground truth label, so image digit category. So in an unsupervised way, and this we clearly outperform the previous clustering. So this is the introduction, and now I'm going to talk about the detail of our method, IMSAT. And IMSAT consists of two parts. It consists of information maximization and self-augmented training. So first, I'm going to talk about information maximization, which is in this direction. So in the previous method, RIM, it basically tried to learn the cluster assignment probability, P of y given x. So x is the data and y is the cluster assignment, by maximizing the mutual information between x and y. Now we want to learn discrete representation probability, P of y1 to yd given x. D is the dimension of discrete representation. And our idea is quite simple. We can just maximize this quantity, mutual information between input data x and discrete representation y1 to yd. However, there's a challenge to maximize this. It's that when we calculate this mutual information, it involves combinatorial summations like this. And this is prohibited. The computation is exponential in D, and when D is large, for example, 32 or 64, this computation is intractable in practice. So we need to approximate this mutual information. And our idea is that to approximate this mutual information by the difference between these terms, and which is we approximate the mutual information up to second order interaction of the random variables. In particular, we see that we can decompose this mutual information into two parts. First part basically maximize the mutual information between input x and output, each element of output y, and at the same time we try to reduce the mutual information. So mutual information measures the statistical dependency between two random variables. So we basically try to reduce the redundancy of each element of discrete representation. And this is now computationally tractable even when the D is large, because it's only quadratic in D. And using our information maximization, we can also learn discrete representation. This can be applied to hash learning, not just clustering. Then I'm going to talk about our method for better regularizing neural networks, which is in this direction. So before that, let me define this augmentation function. So we define augmentation function as a user-specified transformation that preserve the meaning of data. So in this figure, we have some handwritten characters, and we see that by rotating or translating these images, the meaning of the images still remain the same. So we assume that this is predefined by users. Then our regularization, our proposed regularization is very simple. So we first make the prediction of the original data point x. So the prediction is p of y given x, and we augment the data, and which we denote as t of x, and we again make the prediction of t of x. Then our regularization is to try to make these two predictions similar by minimizing the KL divergence between the two predicted probability distributions. So by using this regularization, we expect that the predicted discrete representation exhibits the intended invariance that the user has specified previously. And we can adopt, there are a bunch of other works that also regularize the neural networks by imposing this kind of invariance on the predicted output. So we can employ this idea. In particular, we can consider this augmentation function as the addition of a small perturbation to the original input x. So we add epsilon perturbation to the original input x, which often does not change the meaning of data. And by using this kind of perturbation, we can expect that the decision boundary will tend to lie in the far away from the actual training data points. And so there are two regularization methods previously proposed. One is random perturbation training that randomly sample R from this hyper sphere, and there's another virtual adversarial training that choose R to the direction that the predicted output is most sensitive to. So combining these two criteria, information maximization and self-augmented training, we now arrive at our proposed method, information maximizing self-augmented training. So basically our method do these two things simultaneously, maximizing the mutual information and self-augmented training. So now I'm going to talk about our experiments. So first, I'm going to explain our experiments on clustering. So for evaluation metric, we use the clustering accuracy, which basically try to measure how the obtained clusters correspond well with the ground truth label. And basically the higher the better performance is. And we use this very simple network architecture for the deep neural networks, and other implementation details can be found in my GitHub account repository. So in our experiments, we tested previous method and our method on 8 benchmark data sets that includes image classification data and also a text classification data set. And since we are considering unsupervised learning scenario, we fixed hyperparameters throughout the data set for all the methods. And our proposed methods are highlighted in the red. And for our method, for self-augmented training, we use input perturbation for augmentation function. And we particularly use random perturbation training and virtual adversarial training. And we see that our method that use virtual adversarial training achieved the state-of-art performance on clustering, on the task of clustering on many benchmark datasets. Now, our question is, so we use input perturbation as an augmentation function. Then, do domain-specific augmentation function improve the clustering performance? We try to answer this question. We use the omniglot dataset, which is handwritten character digit recognition dataset. Like some samples are here. And for the domain-specific augmentation function, we use small stochastic affine transformation. So given these data points, our stochastic affine transformation will augment the data like this, which, as you can see, does not change the meaning of data. And by using this client domain-specific knowledge, we show that we are able to actually improve the performance of clustering very significantly. And we see that in the right figure, each row corresponds to the data points assigned to the same cluster. We see that our method is able to find clusters that is more meaningful than the left figure. Then I'm going to briefly explain our experiments on the task of hash learning. So the hash learning basically takes the input data and output the predicted hash bits. And we use 3 evaluation metrics. The higher, the better performance is. And for the dimension of hash bits, we use 16. And we tested our method and previous method on 2 benchmark datasets. And again, hyperparameters are fixed throughout the datasets. And we see that our method clearly outperformed previous methods. So finally, let me conclude my presentation. So in this work, we built on the RIM framework, and we made 2 contributions. We proposed a self-augmented training, which is a better regularization method for regularizing deep neural networks. And we also proposed a more general information maximizing criteria, so that our method is also able to learn the discrete representations. And experimentally, we show that our method achieved state-of-the-art performance in both clustering and hash learning. So for future work, we see that the augmentation function basically encodes our prior knowledge and encodes the invariance of the predicted representation. Then the natural question is, what is effective augmentation function for different types of data? For image, for text, for sequence data, or for graph data. So it's interesting to explore. Okay, so thank you for listening to my presentation.